Good evening, dear viewers. Welcome to another BH Futures webinar. Tonight's honorable speaker is someone I'm sure many of you know quite well, but you might not have a full grasp of all of his accomplishments. Nedim Sladić is not your everyday meteorologist, as he has been interested in the field since he was 14, but understanding the vast potential of interdisciplinary work, he got a computer science degree at the International University of Sarajevo. He graduated in 2019, yet for most of his time as a student, he also worked at Face TV as a broadcast meteorologist, science journalist, and editor-in-chief. In 2019, he was also given the special 2019 Rector Board IOS-BH accreditation process. Additionally, he collaborated with the Federal Department of Civilian Protection during Bosnian flooding in May of the same year. And he even published 2 scientific papers. Tonight, he will tell us a bit about the research conducted for one of them. Namely, he will introduce us to the novel Thunderstorm Alert System. As always, we encourage you all to write the questions in the QA section or the chat, and they will be addressed after the presentation. Nedim, thank you once again for being here.
Thank you for having me on this special occasion and on this webinar. Tonight, I will introduce you as you already said, the novel Thunderstorm Alert System. I will share now my full screen for the PowerPoint presentation. Let me just give me one quick moment. Alrighty, I think you can see it. I will play from the start. Okay, I do hope you see my presentation.
All good.
So this presentation is actually done by me, but on this project, 4 people were actually collaborating together. Those are 3 professors, and each professor is from a different country. And of course, the 4th author is me. As a bachelor student, a student with a bachelor degree. So I will briefly introduce the authors. So the main author and the main person who actually got an idea to design the Notas system, novel Thunderstorm Alert System, is Professor Dr. Vlado Spiridonov. He is an associate professor at the University of Skopje in North Macedonia. I want to emphasize the fact that he was a director of National Hydrometeorological Service in Macedonia during 2004, 2005, and 2006. So those 2 years of his mandate. The co-author is also Professor Dr. Mladen Curic. He is from the University of Belgrade, from Serbia, and he is known for having hundreds of scientific publications that are published in very high impact factor journals. And he also taught at least tens of thousands of students across Serbia and also from some foreign countries. The 3rd co-author is Professor Dr. Bora Jakimovski. He's working at the University of Skopje as well. He's a software engineering expert, and his main interest is grid computing. His role in Notas will be actually producing a website where everyone could see nicely the visualization of our model. Currently, we are using GRATS. I will explain it later. And due to the fact that it's not that visually nice, it doesn't look that nice in the console, Professor Dr. Bora Jakimovski will run this model through the server at University of Skopje, and he will help us to build the website for such occasion. And last but not least, that will be me, a future master student at University of Reading in the UK, and currently a meteorologist for Nova Beha and News Masadega, Bosnia and Herzegovina. So enough of introduction. Let's move to the next slide. So this is the timeline, how everything started. So in mid-2018, there was a first hint that Notas will be designed for detecting the thunderstorms and all kind of severe weather across the southeastern domain of Europe. And the development started when Professor Dr. Spiridonov was at the University of Vienna. He was testing some of the thunderstorms that affected the Skopje region in August of 2016 that unfortunately brought many problems, including that storm unfortunately took at least 20 lives. That was his highest motivation to produce something that will be crucial for the upcoming years and upcoming scenarios, and to reduce every single possibility of losing someone's life. In that case, that was the first hint that Notas will be alive very soon. And in summer of 2019, I talked with the Professor Dr. Spiridonov, and he proposed me to work on such project. I said yes, because I saw that he actually visualized some of those scenarios. Later you will see everything. And I said that would be a good opportunity for me to enhance my knowledge in meteorology. So I was doing my role actually in this project was to analyze such storm scenarios, describe it synoptically. So the synoptics were the focus of my role in this project. And also I did some statistics or statistical data analysis regarding verification of the model, and also detecting if there are some biases that can be reduced. In October 2019, we started with the first draft of the paper. So we were testing still variety of cases. And when we saw that those cases can be actually, that those cases are actually really close to what happened, we said, okay, this is going good, this is going well. We can enhance it because we can use some of the severe weather parameters, I mean, environmental and physical parameters, in order to get some sharper criteria. And we did that. We had lots of equations inside our system. I will explain it also, what does it mean for us having a WRF system. And also we did lots of revisions for such scenarios that we analyzed. Firstly, we focused on the southeastern domain of Europe, but as the time progressed, we were focused also on the Atlantic Ocean, basically on the hurricanes, and also we tried to see if Notas will work in the Pacific and the Indian Ocean. And we were surprised to see that actually it works. It worked for many typhoons and tropical storms that affected Thailand, Vietnam, recently the Philippines, and those results will be presented later. On May 22nd, 2020, we did a revision of our paper that we submitted in March. And on June 9, 2020, the paper was accepted in the Springer Asia Pacific Journal of Atmospheric Sciences, which is under the umbrella of Korean Meteorological Society. So that's a journal that is the part of the Korean Meteorological Society. So it has a higher impact factor. And for 4 weeks later, when the paper was accepted, it was published. On the last bullet point, you can see the link to the paper, to the official paper that is published within the Korean Meteorological Society. Now I will like to show it to you what NOTAS really is. We talked about, I mentioned, to be more precise, I mentioned WRF. WRF is actually a numerical weather prediction model that has a lot of schemes. And because we are talking about having a mesoscale model, we are focusing on some domain. What does it mean? Well, in this case, we were focused on the southeastern part of the Europe, including 8 countries, basically the ex-Yugoslavian countries. And also for running the NOTAS, we need to have some input or some initial data that will be driven. So in our case, WRF is set to be at 5 kilometers horizontal resolution. I will explain what horizontal resolution means, but I want to emphasize the importance of schemes. The schemes are actually the part of the WRF regarding physical and mathematical component. So each of these schemes that you see on the left-hand side, for example, PBL, Thomson, Janicetta, Moni-Nabokov, Cumulus convective schemes, Tivari, Dudia, those are the schemes that include a set of differential equations, or should I say partial differential equations that are already solved within the WRF. Because the WRF is already a pre-built-in system with all of the equations that are already served for you. You can already use them. And those equations are based on the physics and mathematics, which is not a surprise, but you will see that we will cover but you will see that we will have lots of deltas. Well, that explains that we will have some uncertainties within the time frame regarding our parameters that we want to analyze in depth, and that's the reason why we will have lots of deltas, and also we will have some numerical methods like Runge-Kutta, which is widely used in meteorology to actually reduce the lower end errors in our model. When we talk about these schemes, I want to emphasize that these schemes are based for the surface, for the higher level of the atmosphere. So we are focused on the level of the atmosphere that is between the surface and at least 12 kilometers. Where actually the stratosphere begins. So planetary boundary layer is actually the PBL, and it explains what happens in the mid part of the atmosphere, or should I say what happens within the atmosphere, where all of the processes are starting to form and also later to develop. Thomson microphysics is here important because of the aerosol awareness. So we include a little bit of chemistry there. And we have some schemes regarding surface parameterization, for example, Tivari and Janicetta. Those are the schemes that are widely used in regular numerical weather prediction models. And we also have cumulus convection scheme that is actually, as as the scheme already says, we are using it for detecting the cumulus developments, because those are the clouds of the vertical development. When you see all of those schemes, now you can see that this model has a lot of potential, because it is using the most advanced microphysics, because Thomson is considered to be the most advanced microphysics in WRF. And also we have lots of schemes that are helping us to detect the cloud coverage. For example, Dudia is really good in detecting the cloud coverage and to reduce the clarity, I mean the sky clarity, and also it is considered helpful for radiation. Now moving on to the domain. When I'm talking about the domain, I want to emphasize that we have here, you can notice here that we have 3 different numbers. Those are 3, 9, and 27. For example, we have 4 domains for the nested run, because we have 2 types of run modes. That's the single and the nested one. So the nested one is basically having more domain inside the existing one. For the Southeastern Europe, we have a 9 kilometers domain. But for example, if we run the domains in the nested version, we have Macedonia and Bosnia and Herzegovina that are still under the test, but they are run at 3 kilometers. And Europe has been run on 27 kilometers grid. So when we talk about 3 kilometers grid, that means that I have a grid that is covering, for example, if I talk about Bosnia and Herzegovina, then I have a grid, horizontal and vertical grid that is covering Bosnia and Herzegovina. And on each 3 kilometers, I have at least one data point that is interpolating all of that data, and also it detects better than my terrain mask. And terrain mask is really important, and I will explain it in the next slide. So when the domain is set down, we go to the input of our initial data. So we use the data from the existing numerical weather prediction models. Those are, for example, ICON, EU, GFS, and ECMWF. For ECMWF is sometimes really hard to get the grid data. So most of the time we are focused on ICON if there is a domain that covers the grid. And we know that GFS is the global forecast system, so basically it covers the entire globe. So most of the time we use the GFS as our input or initial data, and there we use our environmental and physical parameters, or should I say instability indices. This is important part because we can run it in the single mode or even in the ensemble mode. So in the ensemble mode, we have 15 members. Most of them are consisted within the WRF system, and it covers environmental and physical parameters. That means that we can run our forecast, or should I say Navacast, and I will explain why it's a Navacast, because those 15 parameters will behave as one forecast each. So each of these members will appear as one forecast. That is really important because we are now talking about diagnostic algorithm that needs to detect what kind of alert should be issued for the specific selected area. And here is where Weibull distribution helps us a lot. It behaves on the way of the cumulative density function, but because we are taking into consideration 10 environmental and physical parameters or instability indices, then we use multi-cumulative density function. This is really important because with Weibull distribution that is widely used in meteorology, we can reduce the uncertainty for some development that is already in the phase of shutting down, or should I say the process is dying, and we want to reduce that in the next step, or should I say the next upcoming hour, because we are taking the maximum value for each of these parameters that will be taken into consideration. You will see later what I'm talking about. And when all these parameters have been calculated properly within variable distribution, and this diagnostic algorithm, we get the output, which is the grid and our interpolated, or should I say extrapolated data within the interpolated grid based on the terrain and the domain we are looking at. So this is basically our scheme for our Notas numerical weather prediction model. And now we move on to the next slide, where we will finally introduce what is Notas. So it's Notas is basically a numerical weather prediction model that is based on the VARF. It doesn't matter if it is based on NMM or ARV structure, advanced research for advanced research weather structure, because we can use both of them. NMM is developed within the umbrella of NOAA, or should I say North American, or should not North American, but it's related to North America, National Oceanographic Administration of the United States of America, and it is widely used for forecasting, but ARV is based mostly on the research. So ARV is used for the research, NMM is used for forecasting. We tend to use ARV because of the research purposes. What is the main idea of Notas? The main idea of Notas is to assess the early warning. That's the main part of Notas. I already mentioned that we want to reduce every hazard to the minimum, and we want to have an early warning at least 6 to 24 hours in advance, so the people can have some kind of insight of what is going to happen within the next time frame. Within the Weibull distribution and Weibull algorithm, or should I say diagnostic algorithm, we want to evaluate the storm intensity, which means that we appropriately evaluated the category. So the category goes from 1 to 5. You will see the pictogram later. And this is what I already mentioned, is that Weibull distribution is used to reduce the uncertainty and the biases. It used the instability indices based on the defined threshold. I didn't mention the thresholds already because you will see the thresholds in the table and listed nicely, and it is really neatly described with all of the variables that are used within the formula for the Weibull distribution. For now, we use initial and boundary conditions for from the GFS. So we are driving the initial conditions from the GFS model. Soon, if we found that ICON has the data that is accessible, then we will use ICON in the near future. But I already mentioned terrain mask. Now I want to put a huge focus on this because it's pivotal to understand. The terrain mask is crucial because all of the convective processes, including the thunderstorms, thunderstorm is the convective process, happens above the mountainous regions. On the first 3 pictures that you can see on this slide, we have a terrain mask, or should I say model orography, for the GFS model, for the ECMWF in the middle, and the ICON EU. ECMWF is considered to be the best and most accurate weather prediction model in the world. But recently, for the mountainous regions, Germans have developed this model in the I think it was 2013. Don't get me wrong, there is a lot of data to digest. I think it was in 2013 because the operational run started in 2015 for much of the Europe. So Germans were developing this model, especially for the mountainous region. And you see now why. If you pay attention to the Alpine region, especially near Austria and Switzerland, you can see that you have basically those quadratics. And you can already see that based on the scale, this is not unfortunately accurate. And why is that so? Now we tend to have a model which has a lower resolution. Horizontal resolution must be lower. And why is that so? Well, because we tend to have more data points that can interpolate that specific terrain mask in order to better detect the orography. So these mountainous, I would say, so these mountainous regions should be better rasterized. And as you can see in ECNWF and ICON, when we reduce the resolution from 25 to 9, it's a significant difference. We don't have those quadratics that are not even extrapolated accurately, but we also tend to get smaller quadratics because we have a 9 kilometer for each of these cells. So these quadratics are like cells within this model grid. For ICON, you can see that it is trying to get to the closest terrain mass as it can go. So the higher data points density results in better interpolation of the mask, of the terrain mask. On the next slide, you will see more models that are now within the domain of high resolution. We have a Swiss model, a Super HD model that was developed by Germans, and on the right-hand side, at the third position, we have Notas. I will explain why Notas, although it is driven at 9 kilometers. In ECNWF, or should I say Swiss HD, on the Swiss model, you can see now that the terrain map is nicely visible. We can even detect the valleys, which wasn't the case, for example, with GFS or the ECNWF. Now, when we see that we have Super HD model, then we get a nice terrain detection. Even the northern parts of the country now has been detected with their hills. For example, you could see in the GFS, this part wasn't detected as nearly as good in, for example, the Swiss model. This is really important because we tend to talk about convective processes, and convection happens mostly above the mountainous regions. If we have a model that is not in the domain of low resolution, or should I say high resolution in this case, but with the low horizontal resolution, then we tend to get, for example, if we have this part near Sarajevo. We all know that Sarajevo has at least 4 mountains encircled. That encircles the entire city, but we all know that their height is around 1,500 meters and 2,000 meters. When we interpolate those data with the GFS, we tend to get that Sarajevo is on the mountain. We tend to get the information that terrain mask for Sarajevo is at 1,109 meters. That is not correct. That is not correct. And then we need to correct the models. We need to correct the temperatures. We also need to correct the precipitation, which is pivotal, because we will tend to get convective processes covering the entire grid, entire cell within that grid. And why is that so? Because it didn't interpolated the data correctly, or should I say accurately. And then we need to deduce the amount of precipitation that will fall in Sarajevo, but for example, on some other model that has higher resolution, that won't be the case. You will see that those precipitation will mostly stick to the mountainous region and not even be close to the Sarajevo. So I do hope you now understand why it's important to have a good resolution, or in this case, we need to have a lower horizontal resolution in order to detect those processes more accurately and to reduce the false alarms. On the right-hand side, on the right-hand side, you can see the Notas, and that mask is, I would say, pretty accurate because the valleys are detected appropriately. So that should result in better detection of convective processes. Moving on, I want to show you now the 3D cloud model that is integrated within the Notas. And this was the case with the storm system that happened over Skopje on August 6, 2016. Notice that that those colors and this silver circle that actually showed us that we have a cloud of the vertical development that will be cumulonimbus that started to rise and its equilibrium state where he reached his top was at least 15 kilometers in height. So we are reaching the tropospheric levels where the brightness was at least with the brightness temperature of at least minus 60 degrees, which could produce the significant amount of hail, which is visible in this red colors. Thankfully, this GIF is like is on the loop, so you can see these red colors. They are actually representing the hail, and the green colors are actually representing the rainfall in the specific grid, or should I say within the specific cell. This domain was related to the Southeastern Europe domain that you can see on the right-hand side. So we talked about I mentioned that we have two modes of running Notas. That's the single mode and nested mode. And the selected areas could vary with the horizontal resolution. So so 4 domains in total will not be driven or not be run at the same on the same horizontal resolution. For example, you have Macedonia and Bosnia and Herzegovina domains that are driven with 3 kilometers resolution, still under the testing processes, but Southeastern Europe was tested at 9 kilometers successfully, and the entire European Union, or should I say Europe, was tested at 27 kilometers. It stretches from the Northern Ireland to the eastern parts of Turkey. That's actually the boundaries for European Union domain. If we run in the nested version, then you can see that you can expect for Macedonian and Bosnia and Herzegovina domain to produce very accurate results, and that should be the case, but because model can sometimes have a bug that can be a false alarm. So you will never have an accurate alarm, not accurate, not accurate model. Sorry for this. But if we run in the single mode, then most of the time we run in the Southeastern Europe domain. I already mentioned that convective processes need to have a terrain map and mask that is interpolated precisely. We know, I mentioned that for GFS, for example, for Sarajevo, it's around 1,109 meters, which is not correct. For ECMWF, it's around 700 meters. Okay, reasonable. For Icon, it's around 650 meters, which is getting better and better. For Notas, is around 617 meters. So we can say that is pretty accurate, but it can get more accurate, but that needs more strength for the computer to run, and also when you try to calculate all of those data, then you tend to get something that will take hours and hours to compute, because you're actually increasing the horizontal resolution, or should I say, sorry, decreasing the horizontal resolution, but increasing the quality of the model. And the main motivation was actually forecasting the severe convective processes, and we are based on nowcasting. Nowcasting is the technique that is widely adopted across the globe, especially in the United States. The main idea is to have a forecast that shouldn't be more than 24 hours in advance. So we are focused on short-term ranges in the time frame from 1 hour to 24 hours in advance. We will see some examples later. This is Notas with their 4 domains in when run in the nested version. As you can see, the European Union is basically covering much of the European continent. Sorry, it doesn't appear to cover the Black Sea region, Turkey, although we try to stretch this domain, and now in 2021 we cover some parts of Turkey, at least up to the Mediterranean basin. On the second picture, you can see that we have a Southeastern Europe domain, but I want now you to focus more attention on this interpolation of the mountains in Southeastern Europe tends to reduce the elevation. For example, here we can see our dynamic Alps, but the highest altitude that we can see is around 1,500 meters. Now we tend to decrease the altitude, and that's not good. But still, it can produce accurate results, because if we run in the domain of Macedonia or Bosnia and Herzegovina, now things starts to get interesting. Things start to get interesting, because we see that now dynamic Alps have been detected more accurately. We see that we have red shades, which is around 2,000 meters. So it's detecting, for example, Bjelašnica pretty accurately, and for example, Maglic, and all mountainous regions in the eastern Bosnia. Now you can see why it's important to have a high resolution model in order to get a better mask for the terrain, and thus you can expect that the convective processes will be evaluated more precisely, and for that reason we tend to run when we can in those two domains for Bosnia and Herzegovina and Macedonia, but we tested the Southeastern Europe domain the most, and it really shown accurate results. So we tend to run this SEE domain most of the time, because it is not that time expensive. It's computing less. I mean, it doesn't take that computational strength like it takes for these domains, especially for Macedonia and Bosnia and Herzegovina. I already mentioned those properties of VARF that is also integrated within the Notas. We have a configuration scheme for VARF and data assimilation, and also planetary boundary layer scale dependent scheme that is developed on Yonsei University in China. So those are two authors from Yonsei University, and they're actually trying to explain what happens within the domain of our interest, where the process is starting to develop, and then when the processes start to develop, and furthermore try to stay alive within domain of 12 kilometers. Then we have a cumulus convection scheme. I already mentioned this, and for the surfaces we have Monino-Bukov-Janicheta scheme, because we tend to use these schemes especially above the mountainous regions. In 1994, Mr. Zavisha Janic, he was a professor doctor at the University of Belgrade, detected that this eta coordinates were behaving accurately above the mountainous regions. Also, we have Tavares scheme for surface level parameterization, especially for the daily use parameters. And for Notas, it is important to mention that we have Weibull distribution algorithm that detects our intensity for the storm system, and the category that are based on the physical and environmental parameters or instability indices that are inputted inside the Weibull distribution algorithm. So this is just a tabular representation of our schemes. You have further explanations for each of them. I mentioned Dudia scheme because it is efficient, for example, cloud and clear sky absorption and scattering. So that's the reason we use that scheme. I didn't mention, for example, that this Janic eta is really good for the soil temperature and moisture in 4 layers. It can be even used in the winter conditions because we tend to have fractional snow cover and frozen soil physics. Now you can see that this model is based completely on the VARF system, driven with all equations, partial differential equations that we have already pre-built, but also we add an algorithm that will detect the category and the intensity of our storm system. So the core of the Notas is consisted of 3 main components. We have a mesoscale model, and basically what's the mesoscale model? It's the model that detects mesoscale processes that includes dairy hosts, convective systems, for example, squall lines, mesoscale convective system, mesoscale convective clusters, then fronts, surface fronts, squall lines. But for that, we also need to have an initial data assimilation, and initialization. So the initial data for this mesoscale model will be, for example, the parameters regarding storm relative helicity, bulk Richardson index, KK index, K index, TT index, lifting index or LI, CAPE index, convective available potential energy for upward motion, convective inhibition or SIN, and so on and so forth. I already mentioned few of them. We use 10 of them. You will see in the variable distribution part. And this data assimilation is basically trying to explain us that we need to get that data from some numerical weather prediction model and then assimilate it within our algorithm. Initialization is our grid that you could have already seen, and that grid is composed out of data points. Each data point detects the processes within that cell. Now we have a second component that is our cloud model. We have severe weather parameters for that as well. And you could have seen the 3D representation of that as well. Everything will be useless without our diagnostic algorithm that takes into consideration the severe weather alert. That means evaluating the processes accurately and delivering the final result in terms of the category of the storm system. Now we will briefly talk about cloud resolving model scheme, because this is the part where Professor Spiridonov put a lot of interest and a lot of his time. This wasn't my part of the presentation. So it is a three-dimensional. So we have X, Y, and Z coordinates for height, width, and time. Non-hydrostatic. This model is non-hydrostatic. That means that Newton's equation of motion for the fluid parcel, when the forces are in perfect balance and the net acceleration is 0. So we have a full vertical momentum equation that is really important for the upper layer of the atmosphere. It is time dependent, it is compressible and viscous. So we tend to have a friction, internal friction, especially in the surface, because we know that friction is pivotal for all processes, especially for the gradiental forces, in order to move one such process to some other I will say cell. Yes, we tend to move those processes from one cell to other cell. And also this cloud resolving technique actually resolves convective scales that you can see here. Again, we have a 3D representation that includes dynamics and thermodynamics, turbulences, and microphysics. So cloud resolving system is basically based on the turbulences, because the gradiental forces tend to move from one place to another, and turbulences are important. Microphysics means that we take into consideration some chemical component, that is, for example, aerosol, in order to get precipitation more accurately, because sometimes when you have lots of dust in the atmosphere, you tend to increase the precipitation over some region, and that's what the most model tend to I will say avoid, because I couldn't see in many models that they use aerosol awareness when it comes to the precipitation. And now I do hope you understand the cloud resolving part of this model. I mean, Notas. Now we will talk about the variable distribution. Now you can see the formula for our main algorithm. This is the second component of the of our notas, and this n goes from 1 to 10. Why 10? Because we have 10 severe weather parameters, or in other words, environmental and physical parameters. And variable distribution is used as a multivariate cumulative distribution function because we take into consideration 10 parameters, which are the combined set of physical and environmental parameters. And most of this variable distribution, this curve follows the Gaussian distribution as well. So why we use variable distribution? To flexibly estimate the uncertainty of occurrence for the severe thunderstorms. And that's the reason that these processes are nonlinear. Though atmospheric processes are undeterministic, they're chaotic, and though due to the scalability of our grid and the resolution that sometimes cannot be accurately defined for some larger processes, because sometimes you can have a grid that is 1 kilometer, but the process is widely spread, and that's the reason that lack of explicit grid can sometimes be a problem. So it doesn't mean that when you have 1 kilometer grid can result in a perfect forecast. You will never get the perfect forecast, or better, you cannot expect that you will get an accurate forecast. So we have also different model configuration. This is the important part, because sometimes you cannot use eta scheme for coordinates. You need to use some other scheme, and that mostly depends on the region where is your focus of the research. And also I mentioned that sometimes models can have specific runtime bugs, and the result can vary significantly. I mentioned that the cumulative density function is used, for example, because we are using 10 parameters, we use multivariate cumulative density function, and we estimate the probability that should be less or equal to its threshold value. Why? Because we take into consideration the maximum value for each of these parameters that we have, 10 of them, because we want to reduce that uncertainty and remove the bias. We notice that if we take the maximum value, then sometimes the pre-existing storm system can be nicely visible in the next step, in the next hour, and thus we can get more accurate result for the upcoming weather system, and to see when the system can die, because systems are born, they live for some time and then die, just like humans. You could have seen these variables inside the equation. Most important one is xi, zi, yi, because xi is a threshold for variables. You will see, for example, for the Cape in mid-latitudes is around 3,500. For x0, this is the constant where the distribution of all of our 10 parameters starts, and zi shows the bulk of the distribution. We said that it follows the Gaussian curve, so we have an exponential rise and then it decays. And yi varies from grid to grid point, so from the cell to cell within model run, and gives the pattern of the distribution. So if we see now our table, this should explain more things. For example, for total index, or TT, we tend to take the temperature at 1 kilometer and 500 meters, and to deduce the difference of the temperatures in 5 kilometers, at 5 kilometers on the vertical column, and add a dew point at 1.5 kilometers and deduce with 5 kilometers as well. If we get that TT is around 55 to 60, then we can expect that severe thunderstorms are most likely to happen. We see that most of our parameters happens to be at 0.55. This is what algorithm calculated, but for the rain, you can see that we take into consideration the 1, because in 100% in 100% of the cases you will have the rain. So this is the reason why it takes 100% of the total distribution. As well, I want to emphasize that parameters that are not heavily used in other numerical weather prediction models, except in the ECMWF, those are, for example, bulk Richardson index that is really good for detecting the supercell developments, which means that on our scale from Notas will be a 4 and above, and storm relative helicity that happens to accurately predict the velocity, upward velocity, and also vorticity. So it tends to give us the vorticity insight whether we will have a tornadic development, or at least the funnel cloud that could be developing in order to produce the tornado as its base. Enough of the Weibull distribution. Now, when all parameters have been calculated, when all of the parameters have been reduced with the uncertainty, and when the bias has been removed, we now see that we get 5 levels for each storm, because storms differ from one to another. Here we can see that cumulus clouds are based for the vertical development, because in cumulus clouds, if they are scattered, with most of the time there is a lot of convective inhibition that inhibits the processes of thunderstorm development. But if we have a single cell, then isolated thunderstorm is probable, and it will happen on some local scale. But enhanced convection means that we have a squall line or convective band, which is a stripe within well-organized thunderstorms. We have severe storms that are actually connected within one stripe. You can see that stripe is actually visible on this photo, and these red colors are actually showing us where we have the most intense, I would say, most intense, I cannot come up with the word, I'm sorry for this, most intense development for the storm. This region, for example, should suffer the most, and also these squall lines and convective bands are sometimes associated with the surface fronts that can sometimes bring, I mean, sometimes it can bring a lot of problems in terms of the, sorry for this, in terms of the I would say, just give me a moment, because my head has been stuck after 12 hours. Regarding okay, it can produce damage. It can produce significant damage to many households, and even it can produce significant significant damage to the ecosystem or at least the environment. Moving to the fourth level, which is multi-cell development. Now we can see here ecotops, this almost black color shows the ecotops. Here we also can have potential for tornadic organizations. That means the tornado can organize and develop. And those systems are most of the time widespread, very severe. They bring most of the time significant damage to the properties. And what's important to emphasize, they're well organized and they live very long. Those are for example, mesoscalar convective systems that happens mostly overnight, and mesoscalar convective clusters. You can have those clusters to be scattered all around the grid of your analysis of your forecast. So you can see that sometimes you can tend to have very significant developments that can produce a significant damage in terms of ecosystems most of the time, if those areas are not inhabited. If inhabited, then we have a significant damage to the properties. The last but not least, and we all don't want to suffer this, is the extreme one. Then we have a supercell, which is extremely severe. It lives very long time, and in fact, this category from 4 to 5 was the storm that affected Skopje on August 6, 2016, that brought many problems, claimed at least 20 lives, and that's the reason why we don't have to see number 4 or number 5 or our Notas. Now, this part becomes much easier because now we are more focused on the visualizations. This is how the 3-kilometer horizontal resolution looks for Macedonian grid and for the Bosnia-Herzegovina. In both cases, I took the radar reflectivity, and as you can see, it really nicely reflects the developments above the mountainous regions, especially in the Dinaric Alps. If you focus more attention to the Bosnia-Herzegovina, then you can see that these red shades and orange shades are actually representing the mountainous regions. Hence, we can say that model is really good in detecting the developments above these regions, which was our main goal, and we are really happy that actually that happened. And as you can see here, it really nicely detects the valley of the Neretva River all the way down to the Adriatic Sea. Moving on, I will now run one of the runs of the Notas, so you can see what is actually going on. So basically, I'm running the alert category. So we have categories from 1 to 5, and as you can see, because we have an upper low situated above the Hungary and the northern Serbia, we tend to have anti-clockwise circulation, which brings the humidity. I will run one more time so you can see what is actually going on. So we have an anti-clockwise circulation that brings the humidity from the Adriatic, and then it develops the cloud coverage in the Dinaric Alps that, with the southwesterly winds, they go northwards towards, for example, here in northeastern Bosnia, where we had level 3. This level 3 brought a significant amount of rain in Tuzla Canton, and thankfully this time without any damages, significant damages. This is actually the same. I saw that I had one duplicate. I apologize for that. Now I want to talk about analyzed cases and model scale. It is tested mostly during mid-latitude summer because convective processors tend to develop between April and October because that's the warmer part of the year in mid-latitudes. But we also perform tests in Vietnam, Thailand, the Philippines, for typhoons and tropical storms. Most of the time that was for the Balkans, but we took into consideration the Canada and Paraguay, because professor went in December 2020 to present Notas in Paraguay in Asunción. But Paraguay was the point of interest because of the developments in the Atlantic. And also we took into consideration the hurricane that affected the east coast of the United States. And Notas is basically the east of X concurrent because already east of X, if you type into Google search east of X, you will see that there are some forecasters that tend to give the storm alerts in advance for the next day in order to Europeans to be prepared for some severe weather activity if there are potentials for that. I have to emphasize the important fact, and that's model scale. The model scale is at 0.7 out of 1, which tends to produce 70% accuracy most of the time, which is really surprising, which was really surprising for us. But then when we tested further, then we could see that this model has a lot of potential in the future. Of course, that means for the further upgrades. This is the hits and false alarm. Here are our cities that we analyze. We have at least 15 cities from Italy to Turkey. And as you can see, the false alarm alert was the highest, for example, for Rome and for Budapest. We assume that happens because our grid now tends to lose the signal because it's very close to the edge of our grid. That's the case, for example, for Rome on the eastern side, for Budapest on the northern side, and for Thessaloniki on the southern side. But in the hit rate, we tend to see that most of the time it is accurately predicted for many cities, especially for Dubrovnik, Ljubljana, Podgorica, Sofia, Sarajevo, Venice, Vienna, Zagreb. So we can say that we have a model that can be on which we really rely. This is the cumulative hit rate probability and cumulative false alarm probability. Now you can see the broader picture. For example, the highest hit rate was for Venice, for the northeastern part of Italy. Then it comes Zagreb, Ljubljana, Sofia. Sarajevo is around 0.78, not that bad. But for example, for Belgrade, it was surprisingly very low. It was a 0.67, so two-thirds, two times in 3 trials. Then it will get the hit rate accurately. For the cumulative false alarm probability, we see that Budapest, Rome, and Thessaloniki have the highest rate for the false alarm probability. We assume that it's because the grid narrows down and we tend to lose the signal over those regions. But it is really interesting to see that the lowest false alarm probabilities for Vienna and for Ljubljana. Even Sarajevo, Skopje, and Sofia are on the lowest levels, so which is a good thing, especially for us living here in Bosnia and Herzegovina. Now, I will briefly just mention the bias of the model. We all start from the 1, but the bias is not that significant. It is actually the highest for the Rome. I already explained why. But for example, we notice that for Belgrade, for Sarajevo, and Vienna, surprisingly, it is at the level that is considerable, that is considered tolerable for many tested scenarios. This is in cumulative, all the variables that we tested, for example, Hansen-Kulp score, symmetric extreme score, and the thread score, but I will not pay focus on this because I think that I explained the important ones, that's the hit rate and false rate, and also the bias. Now you can see the true light of Notas. On the upper part of the picture, we have lightning cases for Skopje above the southeastern Europe domain. These red, yellow, and white pluses are basically identifying the thunderstorm and lightning potential in that period. So where the lightning occurred in that specific time frame. If this plus is red and orange, that means that system is shutting down. But if it is white, then that means it's fresh. It is like I cannot say it is already born, but it is born recently. It's born recently. That would be the most accurate description for this. And as you can see, if we pay a close look, for example, on the southern part of the Italy, we see that we have level number 4 and number 5, which really nicely detects the lightning processes, which happens in the next time frame all the way down to the end. And here, this is the important part. For example, for Skopje, at around, let me see what the time frame is, because this covers at 19 UTC, so at 8 p.m. We see that we have a level 4 for Skopje, but we see that this lightning potential has been detected pretty accurately on Notas. So this was the case when Notas shown really accurate results. Moving on to Belgrade case, and as you can see, the same story where we have red shades and purple shades. We have huge amount of lightning, and we see we have here as a horseshoe, which is nicely detected on Notas as well. For Sarajevo case, we see that lightning has been scattered all around the southeastern Europe domain. Thus explains lots of yellow and orange shades. And as you can see, this line, this stripe here, it actually is really nicely detected by Notas because it stretches all the way down to the eastern side of the Bosnia and Herzegovina, all the way up to Kordumbania region, or should I say Krajina region. And I can say that this storm that brought Sarajevo 40 liters of rain, 40 liters per square meter of rain in less than 35 minutes, produced a significant flooding in Basharcia. And we actually used that for the first time. When I used Notas, I was forecasting that storm will hit Sarajevo around 15 p.m., 3 p.m. or 15:00 or 14 UTC, and it happens to be that the forecast was correct. Sorry for this. Next, we have a Thessaloniki case, which was a case when Professor friends called and say, thank you, Professor, for having this model. It saved our lives. Because Solon was badly hit, I mean, Thessaloniki was badly hit with this storm system. And here it gets really interesting. Now you can see that we have a wide part all the way down to Macedonia. From Austria to Macedonia and Albania. But as you can see, these lightning detections really are in line what Notas have been showing for that specific scenario. And here you can see this cluster here. It is actually really nicely detecting Solun, I mean Thessaloniki at level 4, which was really, really badly hit. This is almost the end. And now I want to focus on the hurricanes. We tried to predict the Hurricane Dorian, and we were successful at that because the Dorian was accurately predicted 72 hours in advance before it hit the Bermuda. And as you can see here, this green dot explains where is the center of the hurricane. Of course, you tend to get those higher rates outside of the eye because this is where the most of the processes actually happens, because you tend to suck the air in the lower part of the atmosphere or at the surface, and then you try to pull it up to the higher levels and then to downdraft it, sometimes with very high precipitation rates, which is common for hurricanes and typhoons. Now, if you track the eye of the hurricane, you can see the pattern where it went. It went to the Bahamas, and then it took the direction across the eastern part of the Atlantic Ocean. Now we focus on Typhoon Curic. That was the recent hurricane that appeared. I will briefly show you the animation, and as you can see, almost the same story as it was with the hurricane. The most of the activity happens to be outside of the eye of the typhoon in this case, which explains why the radar reflectivity is higher outside of the eye. And of course, it results that our storm levels are much higher. I will run it for you as well to see where it went. Okay, I think we are near the end. Last but not least, I want to show you also the mean sea level pressure, because when you track the hurricanes, it's really important to see what is the mean sea level pressure inside of the eye that can sometimes drops even below 940 hectopascal. We all know that pressure reduced to the sea level is around 1013, which is significant difference. Now you can see that it dropped all the way down for at least 965, 970. If you pay more attention on these blue isobars, I mean the lines that are connecting the same regions with the same pressure level, then you will be able to see, if you even zoom it, then I mean, you will detect that it is around not 790, but 970 hectopascals, or 965. This was the typhoon Molave. I don't want to pay attention here. I don't want to spend more time on these analyzed cases, but I want to show you where Notas showed his strength, and it's the eye of the storm. If you pay a closer look, then you see that the eye of the storm was pretty accurately forecasted, or should I say nowcasted in this particular case, because it is located in the east of the Vietnam. So we come to the end, thankfully, because I'm losing my breath. I don't know what's happening, but it has been a long day. Don't mind me. So we have I can say that we have a pretty accurate tool for nowcasting and forecasting thunderstorms. We expect that better results can be expected with other numerical weather prediction models such as ICON and ECMWF if we use their input data, which do hope will be the case in the near future. And also we do hope that a web platform will be established very soon, which means that visual upgrades will be visible to everyone in the near future. So that's it for this webinar. Thank you so much for your invitation. Thank you so much for your attention. I do apologize for my hesitations because I'm losing my breath. I'm really tired because this was a hectic week for me, and do hope you don't mind for such I cannot say minor mistakes, but some moderate mistakes. Thank you so much.
Well, thank you for taking the time to share your knowledge with us. And honestly, like those pauses were not even noticeable. You did a great job. So we actually have a few questions from the audience, and since some of them were not able to stay throughout the entirety of the presentation, but we'll watch the rest of the webinar when it's available on YouTube. I will still read them out to you so you can respond. So the first one was, and this was maybe 15 minutes into the presentation, what do you mean when you say that you can use the equations from the WRF?
WRF is the already pre-built numerical weather prediction model, and those schemes are actually pre-built a set of partial differential equations. Those schemes that you could have seen, for example, Yanicheta, Moninobukov, Dudia, PBL, those schemes are set of partial differential equations that are already solved, that are already reduced to the lowest terms that can be solved. So they are not completely solved, but they serve as a base for the numerical weather prediction model that we also use, and that's our Notas. I do hope now that the participant who raised this question understand what I have been talking about.
And what are some of the technologies that you've used to create the system?
Can you repeat the question one more time? I didn't catch it.
What are some of the technologies that you've used to create the system?
That's a good question, but unfortunately I cannot give a I mean, I cannot give a proper explanation to this one, because this is the part where Professor Dr. Jakimovski will take his role. He is our IT guy. He will use, I think he will use pre-existing platform, because Professor Spiridonov also developed the platform for detecting the air pollution, which is really which is based on the heat maps. So we are kind of sure that it will be it will be focused on heat maps, but I'm not 100% sure what will be used for when it comes to technologies. Unfortunately, I cannot answer this question completely, because that's not my part of the work. I mean, it's not my role inside of this project, but Professor Jakimovski is one of persons that are I mean, his role is actually to raise the graphics level to the higher level, and we probably will use the heat maps because colors are, you could have seen the colors are dominant in our presentations.
Well, that's a tip for us to kind of pay attention to how the project will be developing and advancing throughout time. The rest of the questions are more oriented not specifically towards NOTAS, but more towards your own experience as an engineer that went into meteorology. So one of those was, who do you look up to, your role model in life and work?
My role model in meteorology in general is Dunja Matsoko-Drva. She is a Croatian meteorologist who has been working for many years in broadcast meteorology, but also she was serving the position of forecaster inside the Croatian Hydrometeorological Service. I got a nice handouts from her of what I should present, what I shouldn't present, because when you deliver the information, it should be accurate, neat. There shouldn't be the informations that are circulating around the bush. You cannot have space for that. The information must be clear, neat, informative. And also that means that you really have to prepare for your weather forecast in order to present it accurately.
On that note, another one of the questions was, wait, let me just check for a second since there was a related question. How much time a day do you spend analyzing compared to presenting on TV? How much work happens behind the scene?
It depends on the day. Sometimes I can make a forecast in an hour. Sometimes it takes me 5 hours, and sometimes even 12 hours. It depends of the current situation around the Europe, and if I have some cyclonic activity or frontal system that is moving from the northwest, then I'm pretty sure that I will have to spend much time on the analysis than on the textual part. But when I try to encompass everything, then it usually takes me around 30 to 45 minutes to write a report. And sometimes writing report is harder part than the analysis. In my case, for example, my colleague who has been working with me on the Nova BH, he is really good in presenting. So his harder part is analysis than, for example, the presentation part. So there's a reason sometimes why I take lots of time for material preparation. But when I analyze, I really try to focus on the important things and important facts, especially if I have a precipitation levels that are really high. Then I want to precisely define if I can expect 25 or even 50 liters of rain, for example, in some parts of the country. But sometimes due to the uncertainty of the model, if you're not pretty sure, then you stick not to give that information. As I said, there is no beating around the bush, but you really need to deliver an accurate information so everyone can expect everyone can expect what you have forecasted. And sometimes I'm really, really stressed out if the forecast doesn't go as I expected, but I mean, that's normal. That's normal. You will never have 100% accurate weather forecast.
Now there's a personal question of mine. I've read it somewhere on the internet from a very unreliable source that the percentages on weather estimating apps don't really represent the probability of it raining, but rather the percentage of the territory that will be covered by the rain. So I would like your expert opinion on your expert knowledge on what those percentages actually represent.
Don't mind me. I'm just laughing because that's so funny. That's so funny because and at the same time it's kind of wise choice to think that the percentages on our weather apps are actually showing the coverage of rainfall coverage for the specific area. That's not true. It tells us the probability of occurrence in that specific time frame. For example, if I see an umbrella icon at 18:00, or should I say 6 p.m., and there is a 50% chance, then I know that it will rain, it will not rain. Or if it is 60-70%, then I sure know it will rain. There are high probabilities that it will rain in the specific time frame. So that's the true part of the percentages within our weather apps that we have on our cell phones, but also on our search engines.
And I will wrap it up with one question that I believe is of great importance to everyone in Bosnia that actually has any affinity towards geography as a whole and not just meteorology.
Okay.
Thank you. What can other people interested in meteorology in Bosnia do? How to learn, what to study?
To be a meteorologist, you need to finish, or should I say first things first, you need to enroll the geophysics department. So lots of geography, physical, chemical, and not, let me see, let me try to put this in this sentence. There are a lot of geographical subjects from the perspective of physics, mathematics, chemistry, statistics, data science. So it's multidisciplinary field where you can really stick either to the forecasting or assimilating the weather models. So if you're in the meteorology, you can be the presenter, you can work in the hydrometeorological service, you can work as a IT guy who assimilates the weather models, develops weather models, enhance the quality of the models, visualize the data, do researches. So it has a variety of options. It's not just sticking to the weather forecast.
Thank you so much. And I really wanted to hear you say that, because I believe that a lot of students, especially around here, do not realize how much you can actually accomplish when you mix branches, when you do interdisciplinary work. And you are a prime example of something that could be a very great future for our country in terms of the way that young people think and perceive certain careers. So once again, thank you so much for sharing your knowledge and for taking the time out of your busy schedule to be here to talk to us and to present this amazing project that you've been working on.
I'm really glad that I had an opportunity to deliver my presentation, to present it in front of many engineers and many experts in engineering field. But one more time, once again, I do apologize for my English because I'm starting to lose my breath. You could have seen that at the middle of the presentation, I started to lose my breath because this is actually the 12th hour that I have been working and I'm super tired. And also I have been working the entire week and it was really a stressful week for me. Now I do conclude that it was a successful week, and I do hope this presentation was also successful, as was the case with my week. Thank you so much for having me on this presentation.
Have the great remainder of the weekend, and I hope you have a nice rest.
Thank you.
Good night.
Good night.